Hello, hello. Welcome back to another chemistry video. Today, this should be a fairly quick one. We'll see how life goes, but today's video is going to be about phase changes. A lot of what you are going to hear today is things you have learned before, so it's going to be a little bit of a repeat with a little things added on to it. You also may want to have the PowerPoint with you, following along with it, or at least printing it out. There's some great pictures, there's some great examples, and there's a whole lot of links to different YouTube videos and things like that that can help explain some things to you. So let's dive on in. To talk about phase changes, really the first thing we need to remind you of is the different phases of matter. Now, once again, we're oversimplifying. You guys probably learned a long time ago that there were 3 phases of matter. There was going to be solid, there's going to be liquid, and there's going to be gas. All definitely true states of matter. However, that's not it. One of the things some of you may know is there's a 4th one, known as plasma, and that's something you may have heard of before. But what a lot of you may not know is these are still not the only phases of matter. One of the things that we did in class today is we watched a video kind of introducing you to the different phases of matter that are out there. Different scientists seem to have different counts. I don't know what the definitive count is as of today because I'm not sure when you're watching this. But let's just say that there are some that say there are 22 different phases of matter. And they actually recently discovered another one, recently being May 2019. So that is not as simple, once again, as we make it. But we are going to focus on the ones that we see, the ones that we study, the ones that we really kind of have the science background to understand, and that's these 4. So, starting with solids. One of the biggest features you need to know about solids is they have very strong intermolecular forces. Their molecules are tied very tightly together. That gives them a definite shape, okay, and that gives them a definite volume. If you think about your solids, that makes sense, okay? You can pick it up, you can hold it. It is a specific shape. Liquids, on the other hand, kind of have medium intermolecular forces. I know medium is a very random word, but just go with it. Their molecules roll over top of each other. We talked about this earlier this year. So they still have a definite volume. If you pour a liquid into a container, it starts at the bottom and fills it up. But they are going to have a varied shape. Because the molecules are not locked together, they will take the shape of their containers. Gases, on the other hand, have basically crap for intermolecular forces. They are very weak forces. They are pinging all over the place. The molecules are just kind of jumping around, bouncing around. That gives them a varied shape. And believe it or not, it gives them a varied volume. Gases will fill whatever container you put them in. It's not true with liquids. Plasma is one we didn't get into earlier this year. Plasma, to kind of simplify it, is when you have your electrons dissociated from the nucleus. Okay, dissociated from the nucleus. So go back to that kind of traditional model of an atom that you see on different posters and different things like that, you know, where you have your nucleus, and then around the nucleus, of course, you have your electron cloud, and you've got your electrons going in all those patterns. Well, with plasma, your little electrons are still here. You didn't lose them, but they're not following that s orbital, that p orbital, okay, that d orbital. They're not following those paths anymore. Instead, they're very much dissociated from the nucleus. So it's like they're just kind of jumping around in their own little pattern. There's a link on the PowerPoint to a video showing you how to make plasma in a microwave. Please don't do this at home. You will burn down your kitchen. But if you watch the video, you get a really good idea of kind of that undulating look, that very much a vibrational look you get from these electrons not being in strict patterns, but instead of jumping around all over the place, which they sort of do. Another great example, which again, there's a great picture in the PowerPoint, is the Northern Lights. So if you've ever seen the Northern Lights, or if you've ever seen a picture of them, that's an example of plasma. Phases of matter, we kind of always think depend on temperature. And while that's true, it's not just temperature. Other things that really determine what phase of matter something's in, okay, besides temperature, are your intermolecular forces. So whether or not something has a hydrogen bond present, remember hydrogen bound to another electronegative element, A dipole-dipole attraction, that positive and negative connection. The London dispersion or van der Waals forces, where you have the electrons of one attracted to the nucleus of the other. The important part that we know is changing that phase, and that triangle that I just drew means change. Changing the phase definitely requires an energy change. Okay, you are slowing molecules down, you are speeding them up. That's why heat is such an obvious way to really make those changes happen. But it's not the only one. You can also use pressure. So we'll get into this a lot when we start talking about gas laws, but you need to lock in your mind right now that yes, temperature does change the phase, make something melt, make something boil, but it's not the only thing. Okay, temperature is simply one, and it tends to be the most common. So speaking of those phase changes, let's remind you of what they're called. I'll draw you a couple pictures real quick. This right here is a solid. Go ahead, judge my drawing. You know you want to. This right here will be your liquid. Okay, so we still have molecules, but they're much less organized, but they're all here on the bottom. Okay, and then this one over here will be my gas. And of course, it has molecules pinging all over the place. Just pretend there's a cap on this bad boy, and that's what's keeping them from going out. So you need to know phase change names, and I bet you all know them already. Going from solid to liquid, hopefully you know that is called melting. Going from liquid to gas, that is called evaporation. Again, it can be called vaporization, evaporation, you got the idea. Going the other way, gas to liquid is called condensation, and I'm abbreviating because you should know these already. And going from liquid to solid, most of the time we just call it freezing. Sure, you can call it solidification if you're feeling fancy, but freezing works just fine. It is also possible, though, to go from solid to gas and gas to solid without becoming a liquid first. Okay, so solid to gas is something we talked about earlier this year, and that is called sublimation. Okay, that is definitely a possibility. And then gas to solid, we don't ever really talk about much. It's not something that's really exciting. We don't see it a lot, but it's called deposition. Best example of deposition you might ever be aware of, even though you probably aren't going to notice it's happening, is it is possible for water vapor in the air to directly crystallize like on a blade of grass. Now, that's not always how frost is made. Sometimes it is going to condense, become a liquid, and then the liquid's going to freeze. But it is possible for it to deposit directly. So those are your basic phase changes, all right? But the other thing that's important about phase changes, and again, there's a lot of important stuff here, is that they really do vary among substances, okay? So we could spend days talking about how cold it has to be, how hot it has to be, how much pressure you need, et cetera, but you can't really stick everything in one category. The one thing, though, that we can consistently say, and this is huge in terms of this chapter, is that boiling is going to happen, okay? Things going from a liquid to a gas, when your vapor pressure, I'm going to write it out once, and then every other time I'm just going to write VP. Okay, so your vapor pressure is equal to your atmospheric pressure. Now that is a key. That is a walk away. You need to know this from this lesson piece of information. So boiling occurs when vapor pressure equals atmospheric pressure. Great. What does that mean? So if you think about a cup of water, okay, here's my cup of water. Believe it or not, there is a bunch of pressure within this water. These molecules are bumping into each other, and when they bump into each other, that's what pressure is. And there's a certain amount of pressure trying to push them out to become a gas. That's what vapor pressure is. It's how much pressure do I have in this liquid forcing it to be a gas. Now, if you got a cold water bottle, there ain't much pressure going on right there, but there is still some vapor pressure. On the opposing side, you have atmospheric pressure. The air itself in the air, the air itself in the air. Yeah, I said that. The air itself in the atmosphere is pushing down on things. So this is your atmospheric pressure. So there's your atmospheric pressure. So in any open container of liquid, you kind of have a battle. You have your vapor pressure pushing this stuff up to try to make it a gas, and you have your atmospheric pressure pushing it down to keep it a liquid. Well, the only way you're going to boil is when this vapor pressure, is able to equal and then overcome your atmospheric pressure. Very logical if you think about it. Now, a lot of people get locked in thinking it's normal atmospheric pressure. It doesn't have to be normal pressure. It can be whatever pressure that atmosphere happens to be. In fact, that's why we have changes in atmospheric pressure that change boiling and freezing points. Okay? Some of you that bake know that things bake differently at high altitudes and then are here down here in low altitudes. So if this is my mountain and down here this is my valley. If you think about it, up here on my mountain, this is all the air pressure I've got, that little bitty arrow. Down here in the valley, this is the air pressure I've got. So my atmospheric pressure down here in the valley is actually higher than it is up here on the mountain. And that means boiling is actually going to take longer down in the valley. Again, to boil, you have to have your vapor pressure overcome your atmospheric. So if there's more atmospheric, it's going to take more heat and more work to make that happen. Now, let's be real. If you're talking the difference between Stewart's Draft and the top of Wintergreen, you're probably talking like 0.2 seconds different. But there is a difference nonetheless. So what we kind of tie this together to understand is that some liquids are what we call volatile. Okay, if you ever heard the word volatile, people that have a volatile temperament are ready to blow, ready to explode, ready to go off at any moment. Things that are volatile have a very high vapor pressure. There is so much pressure within them, just trying to push them up out of there like they are ready to go. That also tends to mean they have weak intermolecular forces. Okay, again, kind of logical if you think about it, because if they're just bouncing and pushing really hard, they must not have a tight, stable connection. That's going to mean that they have low boiling points. That's what BP is. Okay, on the flip side, a non-volatile liquid is going to have a low vapor pressure. All right, not much kind of pushing it out of there. It's going to have really strong intermolecular forces, a lot of stability, and that's going to give it a higher boiling point. So as you continue through the PowerPoint, you will see a little bit of information about something called the Leidenfrost effect. The Leidenfrost effect will not be on your test, but it's just something kind of cool to look at. So that's why there's some videos. So I'm going to skip that for now and talk about our last topic. Our last topic is, of course, water. Water's the one we typically look at because, you know, it's just amazing. You've got hydrogen bonding that allows it to be cohesive and adhesive. Okay, and one of the things that we talked about earlier this year is that we can look at a phase change diagram. Phase change diagram, or a TP diagram, okay, has temperature over here. And the one we're going to look at right now is not a phase change. We're just going to, not a TP diagram. We're just going to look at temperature versus heat. So you saw this one earlier this year, and we talked about it with water. For the record, it doesn't have to be water. You can make one of these graphs for any substance. Now, the temperatures over here at which the different things are happening will vary, but the shape generally remains the same. This is my solid, this slanted part right here. I'm heating it up. And then when I get to this flat point, this is where I'm melting. Okay? Phase changes do not allow your temperature to change. Notice my temperature is staying completely the same here. It's because this extra heat that's being added as I go up is being used to pull my molecules apart to make me a liquid. That's that slant. As I add more heat, my liquid gets warmer. Then I get up here to my next flat, and this is where I'm evaporating, or vaporization, whatever. And again, you're going to see that the temperature does not change during a phase change. That's another key. Still adding heat, but the heat's being used to pull the molecules apart. And the evaporation flat is usually much longer than the melting flat. Think about it. Solid to liquid, you just have to make them roll. Liquid to gas, you got to pull them all the way apart. So obviously my drawing is not the greatest. What else is new? So there's the gaseous form. You can, for the record, read this diagram backwards. So you start with gas, condensation to become a liquid, freezing to become a solid. So this is the one you've learned before. You need to know it again. But then there's the TP or PT diagram I mentioned earlier. Another way to look at phase changes is remembering it's not just temperature involved. So if we add in pressure as another factor here, what we see is an entirely different looking diagram. This diagram generally has this sort of shape. Now, This is going to vary, the angles and everything, depending on what substance we're talking about. But one thing that is consistent, okay, is looking at the different areas. All of this area over here, this is going to be where I have a solid, okay? All of this area in between these lines, this is going to be where it's a liquid. And then all of this down here, this is going to be where my substance is a gas. So again, yes, temperature is being considered here, but we're looking at the combination of temperature and pressure. So that allows us to look at some other cool things. Generally, this diagram will have a dotted line. It's not always dotted, but lots of times it is. And that dotted line is at 1 atm or normal atmospheric pressure. So sometimes it's labeled 1 atm, sometimes it's normal atmospheric pressure. What we know is that anything on this line right here is between solid and liquid. So any point on this line could be labeled as melting, right? Because you're going between solid and liquid. But the one at normal atmospheric pressure, that's going to be labeled my normal melting point. Again, this is a melting point. This is a melting point. But the one at normal atmospheric pressure is my normal melting point. Okay, and if you wanted to know the temperature, you could kind of track down here and see what temperature it was. Every dot on, in fact, let me erase this line so it doesn't confuse you. I'm going to make that a different color real quick. Let's make it red. Okay, any dot on this line right here would actually, okay, be labeled otherwise. Now, if we look at just this top part, this would be between liquid and gas. That's going to be boiling. If you're looking between solid and gas, these points would be sublimation. So any point on here is going to be boiling. But again, we focus on that normal atmospheric pressure. So that little dot I labeled right there, that's my normal boiling point. But there's some other cool things we can see on this diagram, okay? This point right here, and I know I've made these lines obnoxiously big, okay? But that point right here is where solid, liquid, and gas all meet up together. That is what is known as the triple point. The triple point is kind of an odd concept, but it's the temperature and pressure at which liquid, solid, and gas can simultaneously coexist. There's a video linked to the PowerPoint that shows you cyclohexane. It's actually not at the triple point. You'll notice that there's a lot of phase changes. It's kind of circling around it. So check out the video because it's wicked cool to see. The other point that you will see labeled lots of times is one all the way at this tippy top right here. And this tippy top point is called the critical point. The critical point is basically the point of no return. I know that sounds dramatic, but that's what it is. In order to kind of go back down, to become a liquid again, once you hit the triple point, you have to manipulate both the temperature and the pressure. In fact, this area up here above the triple point is where you are called a supercritical fluid, okay? Again, I've got a couple videos linked to help explain that to you. It's a very kind of high-level concept, but it's the point at which you can't tell the difference between a liquid and a solid anymore, okay? So, again, we're looking at phase changes. We're looking at the interactions between them. I'm going to go ahead and cut this video now. Make sure you know your graphs, and make sure you've got a good understanding of this idea of boiling occurring when vapor pressure occurs. I'll see you in the next one.